Our next speaker has something equally impressive to talk about. Ryohei Funatsu graduated from Tokyo Institute of Technology in 2000 and 2002 with his ME in electronic engineering. Since 2004, he's been engaged in the research of ultra-high definition TV camera systems at NHK's Science and Technology Research Laboratories. He's a member of the Institute of Image Information and Television Engineers of Japan. And what he's going to talk about today is fascinating. It is a 3-sensor, 1.25-inch CMOS center multifunction 8K camera. It can actually record at speeds up to 480 hertz. And again, I'm going to say 480 hertz. When I first read that, I thought that was mind-boggling, but he's going to tell you exactly how he does it. So, Ryohei, the lectern is yours.
Thank you for introduction. My name is Ryohei Funatsu from NHK Japan. Today I talk about the 1.25 inches 3 CMOS multifunctional high-speed 8K camera system. This is the outline of this work. And so the detail is presented at the previous presentation, but this is the parameter values of 8K system. And so 8K parameter values with highest parameter 8K system is called full-featured 8K. And our R&D division is developing full-featured 8K cameras and recorders and displays. So, last December, we started 8K regular broadcast, and we broadcast 12 hours every day. But frame frequency is still 60 FPS at present, but so highest video parameter is 120 FPS. So we have developed, we developed last year 8K high-speed camera and slow motion system for sports content production. And the camera can shoot 240 frames per second video, and slow motion replay server can record the 240 video and output 60 FPS video with slow motion. And recording time of video server is 240 minutes within intra-frame compression. And by using this camera, full-featured 8K 120 FPS video is available using 2-frame averaging. So the slow motion system is widely used in the sports content production. And the first trial is last year, FIFA World Cup Russia. And from the start of regular broadcast, we are frequently using to the sports content productions. So, but we achieved 240 FPS, but some sports with more faster movement requires more frame frequency, and actually some high-speed 4K cameras have already achieved to 480 FPS or more. And another issue in 120 FPS shooting. So in the shooting, we have a problem of low sensitivity because to downsize the camera, the sensor size also reduced, and that results from the shrink of the sensor. The SNR is degraded. And another problem is 20 Hz lighting flicker generated by under the condition of 100 Hz lighting condition. This is no problem in the US, but in Japan, so our power line frequency is 100 Hz, but the shooting frequency is 60 or 120. So there's a mismatch of frame frequency and lighting flicker. So that results from, so 20 writing flicker is generated by the mismatch of frequency and writing frequency. So the objective of this work is to overcome those problems. One is more speed, more high speed, 100 FPS shooting, and another one is image quality improvement under the 120 FPS shooting. So one is reducing the noise, random noise to improve the SNR, and reducing the flicker under the 100 Hz writing conditions. So now I explain the overview of the current 8K camera and image sensor system. This is the image sensor used in our camera. So the key technology is AD converters in the sensor. And to achieve the high-speed AD conversion, AD conversion converter is separated 3 stages. So by separating the ADC, so each ADC timing requirement of each ADC is relaxed, and high-speed AD conversion can be achieved. This is a specification of camera system. Camera system consists of camera head and camera control unit, but our system is still very big and very heavy. This is hardware configuration of camera system. This configuration is developed for 8K 240 and RGB 444 system. And this configuration is basically same to this presentation, but we update the FPGA circuit in the system, and we adapted the new functions. These pictures interfaces used in our camera system. Pictures on left side is USDI. USDI is the standard interface of ST2036, and so the form factor is very similar to the conventional PNC connectors, and we can connect the 8K 120/444 signal by one connection. And in this system, we use 2 USDI connections to transmit the 240 8K video. And the pictures in right side is focal camera cable. So normal camera cable contains 2 optical fibers, but this cable contains 4 optical fibers to transmit the very, very high data rates video signals. So at first, I explained the 480 FPS shooting mode. So to achieve the 480 shooting, image sensor must be operated double speed. So, but we have a program to the timing requirement in the sensor to achieve the 480 video shooting. So in the sensor, we first bypass the original CDS circuit, and so I mentioned the ADC is separated 3 stages, and the first stage works as a CDS circuit. So first stage FI ADC has 2 input source, so 2 input source can relax the timing from high-speed pixel data. And actual AD conversion is operated by second and third ADCs. And these ADCs operated 2 times speed or 1.3 times speed operated faster. And finally output the 10-bit data from the ADC. But the So the sensor output signal bandwidth is very limited, so we need to reduce the bit rate of output data. So in the sensor, so the function of 10-bit to 8-bit compression is used in the sensor. So in this compression, so many codes of 8-bit assigned to the dark range of video, because the human eye sensitivity is human eye is sensitive to the dark level, so we assign the dark signals to the 8-bit, many bit codes to the 8-bit code. And this is the camera head transmission. So the hardware of camera system is same to the conventional 240 FPS system. So we need to reduce the bandwidth of 480 FPS signal. So original signal is RGB 444, but in the camera head, we converted RGB 444 to GBR420 signal. Green is important signal, so green channel signal is all green signals transmitted using two transmission channels, conventionally using green and blue channels. And R and B signals converted to 4K resolution and multiplexed into one transmission channel. By this conversion, we can transmit the 488K signal to the CCU. This is a signal process in CCU. So signal processing is basically same, but additional process unit is added because green signal is twice bit rate. So and R and B signals are horizontally interpolated to use the conventional R and B PROC process unit. And then finally, the camera outputs YCBCR 420 480 videos. So this is a sample 480 videos. This is slow motion. So the video left side is normal speed and right side is 480 FPS video. So you can see the characters on the fan clearly during the loading. And this is the characteristic of 480 FPS mode. Sensitivity and SNR is much lower than I expected. And resolution also degraded compared to the conventional 240 shooting. And we think the SNR and resolution degradation may be caused by the ADC conversion errors, because ADC, second and third ADCs operated faster compared to the 240. And we need to improve the ADC operation to improve the 480 video. Next is 120 FPS random noise reduction mode. So we are developing 120 FPS full-featured cameras. And the first prototype used the 1.7 inches optical system. But the camera head size is very, very heavy, and size also very huge. So we need to reduce the size of camera head. So we introduced the smaller 1.25-inch optical size. But results from the shrink of optical size, the pixel size of sensor also reduced from 3.2 2 micron squared to 2.1 micron squared, and which reduces incident rate and sensitivity, and that degrades the SNR by about 7 dBs. So to improve the SNR, we introduced the multi-sampling technique in the image sensor. This technique uses fast ADC. Fast ADC can integrate the input signal, so multiple times. So, and at the fast ADC, pixel signals sampled 6 times. Same pixel signals are sampled 6 times. And by this operation, the noises generated from the readout path from the pixel to the input of ADCs are reduced by the multi-sampling technique. This is some actual operation of image sensor. So the sampling time is very limited to the ADC, and it depends on the ADC conversion times. And in 120 FPS operation, the AD conversion time for multi-sampling is 0.93 microsecond, and during this time, we can make multi-sampling at 6 times. This is the result of noise reduction effect. By using these techniques, the SNR improved 4 dB using the multi-sampling. Not reach to 7 dB by shrink of optical site, but this technique is very effective to reduce the noise level of the camera. And this is a histogram of dark image, so you can see the effect of multi-sampling from the histogram. So, and so final upgrade is flicker reduction mode at 120 FPS. So this slide illustrates the mechanism of flicker generation at 120 FPS shooting. So when light source actuates at 100 Hz cycle, and shooting is implemented at 120. Then, so the luminance level of video signal is repeated every 1/20 seconds. So it is participate at 20 Hz flicker on the video. This program occurs at 60 FPS shooting, but in 60 FPS shooting, the to set the 1/100 second shutter period is effective to reduce the flicker, because shutter speed and so period of lighting flicker is matched to the shooting time. But in 120 FPS shooting, this technique cannot be used because the exposure time of 120 is shorter than 1/100 second. So we need another technique to reduce the flicker. So this slide shows the worldwide power line frequencies. So in the US, frequency of power line is 60, and video frequency also 60. So there's no program to the mismatch of writing frequency and shooting frequency. But in the areas in 50 Hertz, and so writing equipment without inverters fluctuate at 100 Hertz. So in the area with 50 Hertz area, it has a program to generate flicker, 20 Hertz flickers. And Japan is a very unique country. So west of Japan is 60. In Osaka area, it's okay, so free from flicker. But East Japan power line frequency is 50 Hertz. So in Tokyo area, we have flicker is a very, very critical issue. And we need to overcome these issues. This slide illustrates our proposed method to flicker reduction. To reduce the flicker, the image sensor is operated at 240 double speed, and but each frame exposure time of each frame is different. So first frame is short exposure time with 1/600 second, and the second frame has a long exposure time, and long, short and long and short and long. This frame is repeatedly output repeatedly, and using consecutive three images and summing 3 images, the total exposure time becomes to 1/100 seconds. So this can match to the writing source frequency. By using this method, so little bit overlap each frames, but the flicker is suppressed by this technique. So this slide illustrates the image sensor operation in the camera. So 2 rolling shutter in the camera is used. So 2 rolling shutters, A and B, is used, and rolling shutter A is delayed by 1/600 seconds, and by this operation, the sensor outputs short and long exposure time image repeat alternatively. And we make experiment for flicker reduction. So in this experiment, we used 3 100 Hertz light sources with different waveforms and different phase. And we measured the averaged luminance in the area of A and B and C. Light source waveforms are different, and this is the result of flicker reduction. So the left side is original without flicker reduction graph, and the right side is after flicker reduction. By using our technique, the flicker can be reduced to 1/10 or more. And this technique is very effective for flicker reduction. This is a demonstration of flicker reduction. So you can see the flicker with the flicker reduction. But after flicker reduction, the flicker is completely removed from the flicker. image. Yes, and I conclude my presentation. So in this time, we added 3 new functions to overcome the problems. One is the 480 FPS shooting, double frame frequency, and the noise reduction with 120 FPS shooting, and writing flicker reduction at 120 Hz. But the 480 FPS shooting has a much problem because the image quality is very low and not practical. So we need to improve the operation of sensor to obtain reasonable image quality. And random noise reduction and flicker reduction techniques are very effective to this camera. So, we think that these techniques are very important to the future 8K cameras. Thank you very much.
We have time for one question. If anybody has a question they'd like to ask, please come all the way up to the microphone here. And then we'll continue. We need audio on this?
Anthony Magliotto.
Yeah.
What is the equivalent ISO at those wavelengths? What's the equivalent camera ISO?
ISO sensitivity. Sorry, I can. So I don't have the sensitivity, ISO sensitivity, but I think ISO 100 or more, much lower. And this camera in 480 mode is
Okay.
not practical.
Okay.
Yeah.
Thank you.